Well, hello, my name is Mark Foreman and I'd like to talk to you today about the periodic table. Unlike a lot of things you see about the periodic table, this is not going to be just reciting the periodic table from memory. Now, when I start with the periodic table, I like to start with metal carbonyls, such as iron carbonyl. This gives you a position in the periodic table where iron is. Because we also know that nickel has a carbonyl, this gives you another position nearby. So, nickel has to be 2 spaces away from the iron. Now, if you consider iron carbonyl for a moment, and then chromium carbonyl, because you have 2 extra valence electrons required to make the chromium carbonyl from the ligands, we know that chromium has to be 2 places to the left of the iron. So now we have a total of 3 metals. Now the next thing you'll do is, if you do it my way, is we have to add some more metals. And the next metal we want to add, I think, will be, let me see, manganese. Now manganese does not form a homoleptic metal carbonyl. Instead, you can get manganese bromide pentacarbonyl. And because you get this thing here that needs 1 less electron from the ligands to get the 18 valence electron rule, which means we can instantly place where manganese is, and that should be here between the chromium and the iron. Wonderful, isn't it? Now, things can go a bit better still, because heavy analogue of chromium is molybdenum. If you neutron activate molybdenum, you make molybdenum 99, which decays by a beta emission to make technetium 99M. So, because it's beta decay, that then gives us a position of technetium. The technetium undergoes the internal transition to 99, the ground state of the technetium, which then very slowly beta decays into ruthenium 99. So that now gives us where the ruthenium is. Now, if you so happen to make ruthenium 103, that will then beta decay into rhodium, which gives us now the next item. Now, rhodium is an interesting one. It has a single stable isotope of 103, which also happens to be spin active, but we'll keep that for another day. Now, the next thing we want to add is the next row down. Now, the heavy analogue of chromium and molybdenum is tungsten. Now, tungsten can be neutron activated. I never can remember quite which isotope, but I think it's 188, which I think will then decay into rhenium, which gives you rhenium. And we know that the heavy analogue of ruthenium is osmium. So now we have a small part of the periodic table. Now, if you make ferrocene, ferrocene is a 18 valence electron complex. It's a nice and stable complex. If we make the cobalt analogue, which is the next one along, it's a 19 valence electron complex, which is easy to oxidize in a single oxidation of 1 electron. So that gives us a position of cobalt. Now, nickel, we have that one there. Heavy analogue of nickel is palladium, and then heavier still is platinum. So now we have the central part of the transition metal block of the periodic table. Where some we have to add in here is iridium. Now, if we go a little bit heavier than the nickel, we can then get to copper. Copper is an element which is of great importance to us all in things like copper pipes and copper wires, and so happens to be almost the end of the D block. The actual end of the D block, I think, is actually where zinc is. So we give ourselves zinc here. Now, the heavy analogue of copper has to be silver. Silver and copper are different. Silver doesn't form an easily obtainable +2 oxidation state in aqueous media. It's very oxidizing, while for copper, copper 2+ is easy to obtain. Chemistry changes incredibly again if you then go to gold. Now, if you go to the zinc group, we can then have, going down from zinc, you have cadmium. And then, right at the bottom, you have mercury. And that, I think, wraps it up for a moment.